Now we want to look at linear independence and linear dependence of solutions. Right. Suppose y1 and y2 are two solutions defined on a closed interval a, b, right? Then the two solutions are linearly dependent, right? If there exists C1 and C2, right? Both which are not equal to 0, right? Such that C1y1 plus C2y2 is equal to 0. Right? So we are saying y1 and y2 are linearly dependent if one is a constant multiple of the other. Right? That is, C1 and C2 are not equal to 0. Right? But we can express, like in this case, we can now express y1 to be equal to minus C2 y2 over C1, which we can just write as y1 is equal to some k y2, where one solution is a constant multiple of the other, right? So that is linear dependence. One solution depends on the other. Now moving on to linear independence, right? We are saying on linear independence, we are saying y1 and y2, right, are linearly independent. Y1 and y2 are linearly independent, right? If C1 y1 plus C2 y2 equal to 0 implies that, right, C1 and C2 are zeros to begin with, right? Because one solution is not a constant multiple of the other. So it means for us to have this, then C1 and C2 are zeros. So when we solve for second order differential equations, right, we are going to get two solutions, y1 and y2, but we always seek for linearly independent solutions. This then leads us to define a basis, right, a basis of solutions. So we are saying a basis given a differential equation, y2 prime plus p of x y prime, right? Given y2 prime plus p of x y prime plus q of x y, right, equal to 0. We are given a second order homogeneous differential equation. So a basis on this differential equation, right, on an interval, on the closed interval AB, is a pair of linearly independent solutions, right? So a basis will be a pair of y1 and y2, right, of linearly independent solutions, right, to the differential equation on the given interval. All right, so that is the basis, right, the basis of solutions. Now, out of interest, let's look at an example. All right, show that y1 equal to sine x and y2 equal to cos x, right, are linearly independent solutions to the differential equation y2 prime plus y equal to 0, right? So that's the question. So first of all, we should be able to show that y1 and y2 are solutions, right? And that we can show by substituting the given solution into the differential equation. It should satisfy the differential equation, right? So we have y1 equal to sine x, right? And y1 prime is equal to cos x, and y1 2 prime is equal to what? Minus sine x. So y2 prime plus y will be equal to y2 prime is minus sine x plus y, which is sine x, which is equal to 0, and the differential equation is satisfied. The same applies to y2. If we take y2 and we substitute it into the differential equation, it also satisfies the differential equation. But now our question asks us to show that they are linearly independent solutions. So we just don't end at showing that they are solutions, but we also want to show linear independence, right? So we say that two solutions, y1 and y2, are linearly dependent, right, if one solution is a constant multiple of the other, right? So in this case, this is what we can use to test for linear independence, right? So we have the two solutions, y1 and y2, right? So if we are to express y1 over y2 in this case, right, if they are linearly dependent, right, we should get a constant, right? So y1 over y2 in this case would be equal to sine x over cos x, which is equal to tan x, which is not equal to a constant, right? So in this case, these two solutions, y1 and y2, are linearly independent. So we can make use of the fact that when two solutions are linearly dependent, right, one solution is a constant multiple of the other, right? Or we can make use of the Wronskian, what we are going to talk about now, right? So we want to introduce the Wronskian, right? So suppose the functions y1 and y2 are differentiable on the closed interval a, b, right? Now the Wronskian of y1 and y2, right, is the determinant, right? So we'll write w of x to represent the Wronskian, and is equal to the determinant of y1 of x, y2 of x. Remember, these are our two solutions, all right? And we have y1 prime of x and y2 prime of x, right? And that determinant would be equal to y1, all right, y1 times y2 prime minus y1 prime times y2, right? So if the Wronskian, right, is non-zero, then y1 and y2 are linearly independent. All right. Otherwise, if it is equal to 0, then the two solutions are linearly dependent. So we can make use of the Wronskian for the example that we just considered, right? Where we were asked to show that y1 equal to sine x and y2 is equal to cos x are linearly independent solutions. All right, so the example. All right, so we had y1 being equal to sine x and y2 equal to cos x, and y1 prime would be equal to cos x, and y2 prime would be equal to minus sine x. So now the Wronskian, right, is equal to the determinant of sine x cos x minus sine x, right? That determinant, which is equal to minus sine squared x minus cos squared x, which is equal to minus 1, which is non-zero. Therefore, y1 and y2 are linearly independent.